solutions. So one is that A is just 0, so all that drops out. And B, if B is non-zero, but then cos of alpha A has to be 0. So that means alpha A has to be, what is it, an odd number of pi over 2. Follow that? So alpha A, for cos of alpha A to be 0, and B here is assumed non-zero, so alpha A has to be an odd number of pi over 2. Right? So here, here's your pi over 2, and you've got your A, so you bring your A over. So so let alpha now be n pi over 2a, right? And where n now is odd, right? That makes this 0. Now there's another possibility, is let b be 0, so this term here drops out. Let a be non-zero, but sine alpha a has to be 0, so therefore alpha a here has to be an even number of pi over 2, for the sine to be 0. Okay, so so you can let your alpha then be an integer n pi over 2a, the a because of the a here, right? And there are two sets of solutions. N can be odd integer, or that's for this case, or n can be an even integer. That's for this case. Right? So we have now constraints on alpha. And alpha now is discretized or quantized, right? It can only take on values where this n here is an integer, an odd integer or an even integer. But what is alpha? Right? Alpha is from here, right? Now these are all constants. And so the energy E depends on alpha, right? But alpha is quantized. Therefore, E, the energy, is quantized. Ta-da! That, I mean, may not sound like much, but what I've just said is dramatic. If you think of the history of physics, we've actually now deduced that energy is quantized, which is like the essence of quantum mechanics. I mean, it's so important that the very label of the subject is quantum, quantized mechanics, right? So, there it is, right? So, because alpha is quantized, you only take on discrete values. Therefore, because alpha is square root blah blah. Therefore, the energy is quantized. Now, if you solve now for E, so square both sides, bring h squared over, divide by 2n, blah blah blah, you get a formula now for the actual energy E, discrete or quantized values of the energy of your wavicle in this region, plus or minus a, in this one-dimensional system, right? And there it is. You just you know the value for alpha. You square that, solve for E. Alpha is of this form. You plug it all and do a little bit of algebra, and you come out with this formula for the energy. So we now predicting discrete values of the energy depending on n, where n now is integers 1, 2, 3, ... Right, now a little bit of discussion on why this this formula, how is it relevant? It's just a model, right? It's a bit artificial, but it's somewhat applicable. Like talking about size of atoms and so forth. So if your mass here of your particle, if it's the mass of the electron, I don't know if you can see that. I mean, it's a bit of a test in high definition. Can you see what I'm pointing at there? Does that come out clearly? Are you seeing that as a little c or a little e? It's supposed to be a little e, meaning, so this is the mass of the electron. So if your m here is the mass of the electron, and your a here, this sort of size here, if that a is of the order of 10 to the minus 10 of a meter, that's an angstrom. That's the usual term for 10 to the minus 10 of a meter. and an angstrom is the typical size of an atom, right? So if your A here is of atom sized, right, and your M here is the size of the electron, then the difference in energy levels, say between En plus 1 and En, so En plus 1 minus En, so the difference in energy values between two levels, two energy levels, it works out to be just several electron volt. Now that's the sort of difference of the energy levels that you get in an atom. Right? So that's significant. So that this model is starting to model real-world atoms. Okay? Now note this. Notice that the N here starts at 1. Why is that interesting? Well, because that it did not start at 0, right? It started at 1. Now, N is not equal to 0 because if N were 0, you look it up. If N, there are a couple of reasons why it cannot start at N as 0. Well, we'll use an argument by contradiction. In fact, we'll have two arguments by contradiction. Let's assume the opposite. Let's assume that N does equal to 0. So if this is 0, the energy is 0, right? And if the energy is 0, this is 0, and therefore U is constant, right? From this dE. If that's 0, U must be constant. But by the continuity condition, if U is constant, right? It's just a constant value here. But at this point here, it has to be 0. So that means the value of the constant here in this region has to be 0, right? So your U is 0, and well, that doesn't make any sense, right? Because there's nothing. If U is 0 everywhere, the particle's not even there. Remember, the psi squared gives you the probability density. Well, if U is 0, the density is 0, and therefore the particle is nowhere. And that's a contradiction, because you have to have the integral of psi squared has to be 1, right? The particle has to be somewhere. So if you're predicting U, that it's U everywhere, it doesn't work. Okay, so N cannot be 0. And there's another reason as well, another argument by contradiction, and it involves the Heisenberg uncertainty principle, right? You know this upside down, like the 3 dots, like that's the because sign, right? And if it's like reversed, that's the therefore sign. Okay, so this is the because, right? Let's just use the Heisenberg uncertainty principle in this case. So the wave equal is somewhere in this region. Okay, so the uncertainty in the position is 2a. So in magnitude terms, so it's of the order of size a. All right, and therefore from the Heisenberg uncertainty principle, the uncertainty in the momentum will be h bar divided by delta x, which is a. So you get h bar over a, and that implies the kinetic energy, which is well, let's say the uncertainty in kinetic energy would be the uncertainty in momentum squared over 2m. That's your kinetic energy, right? So that'll be of the form h bar squared divided by a squared 2m, right? But this h bar squared over 2ma squared, have a look here. That's of the order when n is 1. With a few numerical factors, but we're just talking order of magnitude. So the energy then, the uncertainty of the energy is of the order of the